Alright, so today we're looking at the proof of something called the power rule for derivatives. So it's essentially the rule that regards taking derivatives of any function with a exponent or power. So from our limit definition, we did some examples, and for example, x squared, derivative of x squared is 2x, and derivative of x cubed is 3x squared, etc. And we can kind of see a pattern here, but we want to, get a concrete understanding of what this pattern is and where it comes from. So that's what we're going to do. So starting off, we can recall our limit definition. It says that the derivative of our function x to the n is the limit as h approaches 0 of x plus h to the n minus x to the n over h. And so this is from our limit definition. We can use something called the binomial theorem to expand this. So by the binomial theorem, x plus h to the n is the sum from k equals 0 to n of n choose k times x to the n minus 1, n minus k times h to the k. Okay, this is by definition. If you don't know what this means, don't worry. We only worry about the first term, really. Yeah. So we can write out the first few terms of this sum, and we can notice, I'm not going to rewrite it, but you get the point. The first term is x to the n, then n choose 1 of x to the n minus 1 times h plus n choose 2 of x to the n minus 2 times h squared plus etc. Yeah. So we notice that we have a x to the n term at the end of our limit definition, and we can just take this out from this x to the n term, because remember, this whole messy expression is this, which is x plus h to the n. So here we have x to the n, so we can just take that out. So this is gone. And the limit definition is, I'm going to rewrite it. We have the limit as h approaches 0 of n choose 1, then n choose 2, and etc. We can factor out a h from our numerator and denominator. Notice we have an h in every term here. So that becomes the limit as h approaches 0 of n choose 1 plus n choose 2 and etc. So now we have this expression, and you can see it's already much simpler than what we had before. And by definition of n choose 1 is just n. So we have n times x to the n minus 1 plus, all these other terms. And something we can notice is, if we plug in or substitute our limit of h going to 0, all of the other terms behind vanish. For example, this term has h, and everything will have h by definition of the binomial theorem. So all of these terms effectively go to 0. So we can be left with just n times x to the n minus 1. And so that is our power rule for derivatives. And to recap, it says that the derivative of any x to the n is nx to the n minus 1. So let's do some examples. Question 1, we want the derivative of 3x squared, for example. I'm going to give you like 1 second to do this, and then you can pause the video if you want, but it should be pretty quick. Alright, so remember that constants can be ignored during differentiation, so we can do 3 times derivative of x squared, and this is 2x to 2 minus 1, which is 3 times 2x to the 1, which leaves us 6x, and that is the derivative of 3x squared. Now for the second question, let's say f of x is 4x cubed plus 3x squared plus 4, and we want f prime of x. Remember, this is just another way of saying the derivative of f of x. Again, you can pause the video if you want. So how we do this is, I'm not gonna keep writing out all the steps, but you can ignore the constant first. Then do your power rule. So you have 3 times x to the 3 minus 1. Then remember differentiation, addition and subtraction is, they're alone, so you can treat each term by themselves, so you don't have to worry about how they work together. But during multiplication and division, you have to treat them as a whole. So now we can just think about the derivative of 3x squared, and we already did that, and it is 6x. And the derivative of any constant is always 0, because remember what a derivative is the slope of any function, and if we have a function with a constant y value, the slope will always be 0. So, derivative of 4 is just 0. And this gives us 12x squared plus 6x as our derivative. And yeah, that's the power rule. It's probably one of the most important rules, and you use this a lot. So yeah.